Hello dear students, and now we are going to do a small numerical example on the analysis of flanged beams. So we have taken a question, and in this we have to calculate moment of resistance for the given following beam, and this is a T-shaped flange beam, and this T-shaped flange beam has already being provided with all the dimension values, like df is equal to 100 mm, so depth of flange is 100 mm, and width of the beam in the web portion bw is equal to 250 mm, and effective depth small d is equal to 500 mm. Here effective width of flange bf is already calculated, and bf is equal to 1000 mm, so we need not to calculate the effective width flange in this case. And it is also provided that we have used 5 bars of steel bars of diameter 25 mm. Okay, and we can use M20 concrete and Fe 415 steel, and this steel is also known as Tor steel. Tor is because a company from the Luxembourg, and it has been named as Tor, and it is also known as H by SD steel, high yield strength deformed bars, or it is also known as cold twisted deformed steel. Okay, so there are different names for Fe 415 and Fe 500 steel, and they can be called as H by SD steel, and they may be called as CTD steel, or they may be called as Tor steel. Okay, so there is not much difference in all of these three cases. So we have all the data written here, and in this case we have taken Fy is equal to 415 Newton per mm square, and then the value of FCK is equal to 20 Newton per mm square, and effective width of flange is 1000 mm, and we have already mentioned that we are not going to calculate separately effective width of flange, because that exercise, if it would have been required, that then we must have to do the calculation of width of flange first, and that we have discussed how to do this. But here it has already been provided, so we can move forward. Then we have calculated the area of steel reinforcement AST in the tensile zone, and this is a singly reinforced beam. So this is 5 pi d square by 4, and diameter of bars is 25 mm. So this is the total area of steel reinforcement, comes out to be equal to 2454.4 millimeter square. Okay, now we first of all we assume that the neutral axis lies within the flange. Now this is a very simple case. The neutral axis is lying within the flange, so that means this is the neutral axis. Okay, somewhere lying here. So if it would have been true, then the calculation of compressive force is very easy. Okay, so we just apply the equilibrium of forces. So at neutral axis we have done compressive force equal to tensile force, and compressive force will be simply as we used to do in the case of singly reinforced beam, but here we have used the value of BF, effective width of flange, not the width of beam in the web portion. Okay, so this we have to keep in mind, and it has to be equated with 0.87 F by AST. And if we calculate the value of XU, okay, from this equation, then it comes out to be, since every data is given already, then it comes out to be 123 millimeter. Okay, and how much was the depth of flange? Depth of flange was 100 mm. Okay, so depth of flange is 100 mm, and the depth of neutral axis is 123 mm. That means the depth of neutral axis is more than the depth of flange. So our assumptions is not valid. For neutral axis to be within flange, it should satisfy the condition xu less than or equal to df, depth of flange. But this is not true in our case. So our assumption that neutral axis is within the flange is wrong. That means neutral axis lies outside the flange. Now this is clear that our neutral axis is lying outside the flange. So there are two possible cases in this case also, and whatever cases which I have already discussed in the previous videos, they all are mentioned in the IS 456 also. And if you look into IS 456 annexer G, it is on the page number 96 of the IS code, then you will find all the things written there also. All the equations, all the calculations for moment of resistance is mentioned there for the different cases of flanged beams. So even if you do not see, if you just have watched the video, that is more than sufficient. Okay, so there are two possible cases when neutral axis is lying outside the flange. The first possible case is that the flange is uniformly stressed. Now when we say the flange is uniformly stressed, that means we are considering that the extent of rectangular stress distribution of concrete compressive force is more than the depth of flange, or 3 by 7 of xu is larger than depth of flange. See, when it happens 3 by 7 xu exceeds the depth of flange, that means we can say that the entire flange is stressed by the rectangular part of the stress block. Okay, but if it is not true, that means 3 by 7 xu is less than depth of flange, then of course the flange will be stressed, but it will be non-uniform stress, okay, over the flange. So we will be taking first of all the simpler case, that is the 3 by 7 xu is larger than or equal to df. So the first assumption is this: we have assumed now again that the flanged portion is uniformly stressed. Now let us check whether it is true assumption or not. So it means that 3 by 7 xu will be larger than or equal to depth of flange. Okay, so now again we can apply the equilibrium equation, and in that we just equate the compressive force equal to tensile force. And see, the calculation of tensile force is not at all difficult in any of the cases. It is always going to be equal to 0.87 F by AST. Okay, whereas the value of compressive force in this case will be equal to, as we have discussed in the previous video, there were two simpler figures. One was a rectangular beam, and in that width was equal to width of the beam in the web portion BW, and depth was the gross depth. Whereas in other case we put it simply a flanged region, and from that we have already used the BW portion. So the width of flange will be BF minus BW in the figure 2, and depth of flange will be DF, and the value of lever arm in figure 1 will be D minus 0.42, whereas in other case it will be equal to small d effective depth minus DF by 2. Okay, so this was the figure which we have to keep in mind. Now the same thing is done here. We have added the compressive forces contribution from figure 1, which is equal to 0.36 FCK BW, width of beam in the web region, multiplied by XU. Okay, and here we have added it with the contribution of compressive force from figure 2, which is equal to 0.446 FCK, because the flange is uniformly stressed. So this stress value is multiplied with the area of flange, and area of flange is BF minus BW multiplied by the depth of flange. Okay, so from this we can very easily calculate the depth of neutral axis xu, because only xu is unknown in this equation, rest all the datas have been provided. Okay, so if we use all those datas in the above equation, so we can easily solve for the value of depth of neutral axis xu, and xu comes out to be equal to 120.6 millimeter. Now our assumption was that 3 by 7 of xu should be greater than or equal to the depth of flange. So we again do it 3 by 7 xu, and it comes out to be 51.7 millimeter, which is not greater than or even equal to depth of flange. So we can conclude that again our assumption was wrong. So do you feel the interest behind this question? Isn't it interesting? Because all the concept that we have discussed in the analysis of flange is coming into application in this simple problem only. Okay, and all the step by step procedure is done. Okay, so this calculation is a little bit lengthy because we have used all the cases possible in this case, but if our first assumption would be right, then we would rightly go for the calculation of moment of resistance. But since our assumption has come into wrong decision in the both cases, so we will go for the last case. Okay, and here 3 by xu by 7 is less than depth of flange. Okay, so we can say that the flanged portion is non-uniformly stressed. Okay, now it is proved. So we have discussed that IS code also recommends to use the equivalent flange depth. Now what is equivalent flange depth? Gamma f or yf is said to be equivalent flange depth, and if we use this value of gamma f in place of depth of flange as in the above equations, then we can arrive to the exact values of solution in this case. Since this case becomes complex because the flanged portion is non-uniformly stressed, so the code provides us this simple value of yf to use in those equations and quickly arrive to the solution. So we have put the value of yf is equal to 0.15 xu plus 0.65 df. Now again we apply the equilibrium of forces at neutral axis, and here compressive force is equal to tensile force. So when we put all the values, and tensile force is going to be same again 0.87 f by ast, and in the equation of compressive force everything is same as earlier, 0.36 fck bw xu plus 0.446 fck bf minus bw into depth of flange has been replaced by equivalent flange depth. Okay, so here we have used the value of gamma f, and in this we have solved for the equation for the values of xu. Now when we go for calculation of value of xu, then all the data are provided, but if you see the value of gamma f is in itself a function of xu. Okay, I hope this must be appearing again xu here again. So we have to do small interchanging of all the values, and then we can easily solve the equation. It is a linear equation of one variable only. Okay, and on solving we get the value of xu is equal to 160.97 millimeter. Okay, so if we do 3 xu by 7, and it comes out to be 68.98, which is less than depth of flange. Depth of flange was 100 mm. So our assumption is now finally it comes out to be right. So as we have assumed that our flange is non-uniformly stressed, and 3 by xu by 7 is less than the depth of flange, and this comes out to be right. So our assumption is right, so we can choose this value of depth of neutral axis xu, and this is our answer. Okay, no, we have to decide which type of section it is. So first of all, we have to calculate the limiting depth of neutral axis, and limiting depth of neutral axis can be simply obtained by using the effective depth, small d. And which type of steel it is? Fe415, and for that the value of XU limiting is 0.48 d. Okay, and the depth of neutral axis is coming out to be 240 mm. Okay, so this is the limiting depth of neutral axis, and we can easily compare the value of the exact depth of neutral axis and the limiting depth of neutral axis. So we can see this is the exact depth of neutral axis and this is the limiting depth of neutral axis, and if we do a comparison, XU comes out to be less than the limiting depth of neutral axis, isn't it? So we can say our section is under reinforced section. Okay, and here we have also calculated the value of gamma f. Gamma f is equal to 0.15 XU plus 0.65 df, and it comes out to be gamma f is equal to 89.14 mm. So we have to use this equivalent depth of flange, and it is equal to 89.14 mm. Okay, we need not to be using all the time this depth of flange 100 mm. No, we have to use the equivalent flange depth only in the equations. So let us see, in this case of under reinforced section, now we have to calculate the moment of resistance. So moment of resistance can be calculated if we use the compression side formula. Okay, so we have just used the compression side formula and we have multiplied the corresponding compressive forces with their corresponding lever arms. So this is the corresponding value of lever arm corresponding to the compressive force in figure 1, 0.36 FCK BWXU is multiplied by D minus 0.42 XU, and this is the value of compressive force in figure 2, and this has been multiplied by the corresponding lever arm in the figure 2, D minus gamma F by 2. Okay, so when we use all the values, since all the values has been provided now and our assumption is also right, our section is under reinforced section, so we can use the value of XU is equal to 160.97 mm and the value of gamma F equal to 89.14 mm. So using all these values, we can easily calculate the value of moment of resistance, which is the capacity of the section to resist moment, and it comes out to be 596.87 kilonewton meter. So this is our exact value of answer. Okay, so this is how we step by step do the analysis of flanged beams. So we will be discussing on the new topic of shear, torsion and bond also in the upcoming videos. So till that, stay tuned and stay safe. Thank you.